Welcome to lesson number 4 of our review chapter. Today we're going to be reviewing trigonometry. So there are a couple things that you need to know from trigonometry in Math 12. You need to know how to deal with radians. You need to be comfortable working with your identities, and you need to be able to prove things. So you need to understand what a proof is. The other thing that would be helpful to know is your special radian values or your special triangle values. So if you don't know those, I would make sure that you review those as well. So there are lots of practice questions at the bottom of today's notes. There are questions from your Stewart Appendix D, which is a new handout. There are practice questions at the end of today's notes booklet. And then also there is an additional review booklet, Trig review booklet that I have given you, which does more of the exact value, refreshing your special triangles and solving some equations stuff. So there's plenty of review on Trig you can do. It is quite a big section. Um, as you go through calculus at the AP exam or university, they're going to assume that you know all of this. They're not going to give you any special triangles. Half the time you won't have a calculator, and they're definitely not going to give you any of the identities. So it would be a good idea to start refreshing your memory of those and getting used to seeing those in some questions. So first, let's review radians. So if you have a circle with some radius r, you also have an arc length that goes around the outside of that circle. And 1 radian was just a little bit over 50 degrees. And so if this is a unit circle, the length of the arc is the same as the radian measure. So just a refresher, you would have not spent a lot of time on this, and you won't see this much in calculus, but it might come up. So if you have A is your arc length, this is theta times r. So A is the arc length around the outside of the circle here. This would be our A here, okay? And r is your radius of the circle. And theta is the central angle in radians. So if the angle is not in radians, you must convert it. Also a reminder that pi radians is equal to 180 degrees. So if you want to add some measurements on this quadrant system up here, you've got 0 or 2 pi radians on the positive x-axis. You have pi over 2 radians on the positive y-axis. Pi radians is on the negative x-axis, and 3 pi over 2 radians was on the negative y-axis. So we're going to try just a couple questions. If I want to find the length of minor arc AB, that means I want this length here. Okay. Again, A is equal to theta times r. Theta must be in radians, so we need to change the 60 degrees into radians. To do that, we would do 60 degrees times pi over 180, which gives us 60 pi over 180, or pi over 3 radians. Once we have that, we can plug that into our theta. Our r is 12, so I end up with 12 pi over 3, or 4 pi. We have no units for our radius, therefore we have no units for our arc length. Arc length and radius are both distances, so they share the same units. Again, we're looking for the arc AB, which would be this arc here. We've got our theta in the middle here is 3 pi over 5. And our radius here is 1. Our arc length is theta times radius, which for us would be 3 pi over 5 times 1, which would just give us an arc length of 3 pi over 5. Again, we were not given units for our radius, therefore we have no units for our arc length. The next question is saying, without a calculator, find the value of secant 11 pi over 4. So first, as soon as you see a pi over 4, you should realize you're dealing with a special triangle. So you have two special triangles. Special triangle number 1 was pi over 4, 90 degrees in the corner, 1, 1, root 2 for your side lengths. Your other special triangle was pi over 6, pi over 3, 90 degrees in the corner. And this one was 1, 2, root 3 as your corners. You might also remember this one as being 45 degrees, 90, and 30 degrees, 60 degrees, 90 as well, but the same side length apply. So first, secant is the same as 1 over cosine 11 pi over 4. So what I really need to do is I need to find cosine of 11 pi over 4. So cosine of 11 pi over 4, well, 11 pi over 4 means that we've rotated around an entire circle. That would be 8 pi over 4, plus a little extra, and landed in quadrant 2. What that means is that my pi over 4 is my reference angle, so I need the first special triangle I have here on the left. My side lengths would be -1, 1, and root 2, because we are in the negative x-axis. And cosine of 11 pi over 4 is adjacent, which is -1, over hypotenuse, which is root 2. We know secant is the reciprocal of cosine, meaning that secant of 11 pi over 4 would be root 2 over -1, or negative root. So just some reminders. Secant theta is 1 over cosine theta. Cosecant theta is 1 over sine theta. And cotangent theta is 1 over tan theta, or cosine theta over sine theta. And those are on your little trig formula sheet I've given you as well, but you shouldn't need a formula sheet for those at this point. So the first thing for this one, you must know your special triangles or you can't really go anywhere. The second thing is you need to know that secant is 1 over cosine. And the third thing would be you need to know which quadrant 11 pi over 4 terminates in, so that you can actually draw your triangle and find cosine and therefore secant. So just a review of our trig identities, we've got a bunch here. The first ones that you will use the most probably are the Pythagorean identities. So our basic one is sine squared plus cosine squared equals 1. There are two others as well, and we can find these easily by dividing both sides of our basic one by cosine squared. So if I divide everything by cosine squared, I end up with tan squared in my first term plus 1 equals secant squared. And that's where I get this middle one from. Okay. If I were to divide everything by sine squared, I would be able to get the third one. Okay. So you don't necessarily need to memorize them all. You should at least know the very first one, but you would be able to figure the other ones out by rearranging. Also, just a reminder that sine squared of alpha or theta or x is the same as sine of alpha or theta or x all squared. So this is not the angle that's being squared, it's the ratio that's being squared. Also, the same applies for cosine, tangent, secant, cosecant, etc. Okay, so just notation issues there. We also have your sum and difference and double angle identities. So just a reminder, if you have sine of alpha plus beta, this does not equal sine alpha plus sine beta. You cannot distribute the sine into the brackets. Sine is not a number. Sine is not a variable. Sine is a function. Or cosine or tangent into the brackets. Okay, so if you see things adding in brackets or subtracting or whatever, you cannot just distribute this in. You must use a sum difference double angle identity. Okay. Also, we've got double angle identities here. You can prove these using the sum and difference one, which we're going to do in a moment actually. And there are three different choices for cosine. For the cosine double angle identity, you should be comfortable with being able to choose which identity is best for you to use. So if we want to actually try doing some of these questions, the first one is we're going to prove the double angle identity for sine. Okay, so I want to prove that sine 2 theta is equal to 2 sine theta cosine theta. That's what I'm trying to prove. So what this means is I need to be able to use maybe another identity to show that this is true. Okay. So I'm going to work on the left-hand side here. So I'm going to rewrite this as sine of theta plus theta. Okay. Because 2 theta is the same as theta plus theta. Now this is a sum identity, so I can use my identity from up here, this guy. Okay. With my sum identity, this means that this is equal to sine theta cosine theta plus sine theta cosine theta, which is the same as 2 sine theta cosine theta. So it's almost like you have this one is your alpha and this one is your beta. Here's alpha, beta, beta, alpha. Okay, it's just that alpha and beta are the same here. Okay, and that's it. We're done. We proved it. There, two sides are equal. Okay, so a reminder, as soon as you see the word prove, this means you cannot work across the equal sign. You can't move things left to right. You need to work on each side in isolation to show that these things are true. So next, without a calculator, find the value of sine of pi over 8. Okay, so what I'm going to do is I'm going to start by, maybe I don't need a pi over 8. Maybe I'm going to rewrite that. Okay, if I wanted to find this to be something else, I could think of, well, is there something I could do where I can add two things together to get pi over 8? Is there something I can do where I could double something to get pi over 8? And the answer is probably not initially, right? Not right off bat. But if I want to find sine pi over 8, it's telling us we could use this identity. So I'm going to plug pi over 8 in where the theta is. So I'm going to have cosine, oh, I don't want to use red. I'm going to have cosine 2 pi over 8 equals 1 minus 2 sine squared pi over 8. Okay, I'm trying to find this. That's what I want to isolate. Okay. On the left, this is the same as saying cosine of 2 pi over 8 or cosine of pi over 4. And this is 1 minus 2 sine of pi over 8 squared. Now cosine pi over 4, we know this. This is 1 over root 2. Okay, if you don't remember, you can draw your special triangle. Okay, and then I've got 1 minus 2 sine pi over 8 squared. All right. Now, I want to find sine pi over 8. That's what I'm trying to get by itself. So I'm going to move the 1 over. Okay. Now you might want to make common denominators here to make this just not quite so terrible. Divide both sides by -2. Okay. Now, again, you can simplify this a little bit if you'd like. You can do a couple things. You can divide the top by that negative and rewrite this as root 2 minus 1 over 2 root 2. Or you can rationalize, which would give you root 2 minus 1 times root 2 over 2 times 2, which would give you 2 minus root 2 over 4. Okay, all of those are okay, but so is that very initial one. And we're not quite done. We still need to square root both sides. So if I square root both sides, I'm going to get the square root. And normally I'd have plus or minus square root of, I'm just going to use the most recent one, 2 minus root 2 over 4 equals sine of pi over 8. But because we have sine of pi over 8, sine of pi over 8 is in quadrant 1. So this must be positive, this ratio, because sine is positive in quadrant 1. So this is just going to be the positive square root of 2 minus root 2 over 4. And I can actually square root that 4 and rewrite this as root 2 minus root 2 over 2 equals sine pi over 8. So again, when you look at this pi over 8, we have to figure out what are we going to do. It's not a special triangle, but it's asking us to do this without a calculator, which tells us we can use special triangle values. There's nothing I can double to get pi over 8 though. None of my special triangles, if I double those values, will I get pi over 8. The other thing I could do is I could say, well, is there anything I could subtract to get pi over 8? You can make common denominators with pi over 8 and all of our special angles and say, are there any of these I can take a look at and subtract and actually get the value I want? The hint here is really necessary for us to move forward for this question. So this would be a difficult question to try. Just a reminder of what your graphs look like. So our domain and our range for sine and cosine are the same. They both have a period of 2 pi, but they are phase shifted from each other. So they don't look quite the same. The zeros are different. And where our graph is placed, horizontally is different. They both have a max of 1, a min of -1. And they both have a domain of all real numbers. Your tangent graph has asymptotes at all the pi over 2 values. So at pi over 2 plus n pi. So n must be an integer. So your teacher might have used an I for integers instead of z in Precalc 12, and that's what your textbook would have used as well. But z is actually the correct letter we should be using. So you have, again, asymptotes at the pi over 2's, the integer values of pi over 2's. And then you have these funny little curve looking things where you have a range of all real numbers. This thing is going to go up and down forever. So if I want to find the domain of something like cosecant 3x all times 2 minus 1, if I want to do this, what I need to figure out is, okay, so I need to try and find my restrictions. That's what I'm being asked for. I'm being asked for what are my restrictions here, okay? So I need to take a look and say, okay, well, I know that cosecant is the same as 1 over sine. So I'm going to rewrite this as 2 over sine 3x minus 1. Okay. So now we know that on the bottom here, we have that sine of 3x cannot equal 0 because you cannot have 0 on the bottom of a fraction. So what we need to do to find our non-permissible values is we need to figure out, well, when would sine 3x actually equal 0? Well, this would equal 0 if 3x is equal to 0, pi, 2 pi, etc. All the x-axis values, right? So if we take a look, sine is equal to 0 here and here. Well, this is 0, pi, 2 pi, 3 pi, etc. Okay, so we could also say that this means that 3x would equal pi n, where n is an integer. Okay. However, the problem here is that we want 3x to not equal these things, but also we're trying to figure out the domain, so we need x isolated. So I can divide both sides by 3. So that means that our domain is actually that x cannot equal these things, because if x does equal pi over 3n, sine 3x will equal 0. So x cannot equal pi over 3n, where n is an integer. And this also helps us find asymptotes, by the way. Our asymptotes here for this function would be at x does equal pi over 3n, where n is an integer, because those would be vertical lines, x asymptotes, vertical asymptotes at all the pi over 3n. So one of our other things that we looked at in Math 12 was solving trig equations. Okay, so if you were to solve the equations, if you can, you want to try and rewrite everything as sine and cosine first. So for this one, we would have a choice which we want to isolate. We know that we have a Pythagorean identity that says that sine squared x plus cosine squared x equals 1. And that means that sine squared x is actually equal to 1 minus cosine squared x. Or we have that cosine squared x is equal to 1 minus sine squared x. So we can actually replace the cosine or the sine in this solving equation with a Pythagorean identity. Now, when it says solve, this is not a proof. We're trying to get x by itself and figure out what x equals. So we have two options. So option 1, replace sine squared x. So if we do that, we're going to have cosine squared x minus 1 minus cosine squared x equals 1. This gives us cosine squared x minus 1 plus cosine squared x equals 1, or 2 cosine squared x minus 1, 1, or 2 cosine squared x equals 2, or cosine squared x equals 1. If I square root, I get cosine squared x, cosine x equals plus or minus 1. And that happens on either the positive x-axis, this is where x would be positive 1, or the negative x-axis, this would be x is negative 1. And this, when cosine x is 1 on the positive axis, our angle would have to be 0, 2 pi, etc. If we're on the negative axis, cosine x is negative 1, x would be pi, 3 pi, etc. So this means that cosine x equals 1 when x equals 0, because we have this restriction here. And cosine x is negative 1 when x equals pi. Option 2 would be to replace the cosine squared. Okay. If we do that, we would have 1 minus sine squared x minus sine squared x equals 1, or 1 minus 2 sine squared x equals 1, or negative 2 sine squared x equals 0, or sine squared x equals 0, or sine x equals 0. Sine x equals 0 on the positive x-axis or the negative x-axis. So again, this would be 0, 2 pi, etc. This would be when x is pi, 3 pi, etc. Due to our restrictions, x would be 0 and pi only. Okay. So lastly, we're going to do some proving. Okay, this will be our last question for today. Right. So when you are proving something, a reminder that you cannot move across the equal sign. You must work on the left side and the right side independently. So I find it helpful to literally draw myself a wall that I'm not going to move across. So I also find it helpful, if I can, to change everything to sines and cosines first. So on the right-hand side, I'm going to change this to be 1 over sine my angle plus cosine over sine of my angle. And then I'm going to rewrite this as 1 plus cosine over sine because they have the same denominator. We can combine that to 1. Now, the problem I have here is that the two sides are not equal, so I must do some further manipulation. You learned about a couple different techniques in grade 12, one being factoring if necessary, and the other being multiplying by the conjugate. So we've already talked about conjugates of radicals. We also have conjugates in proofs. So if I look at the left and the right, they look sort of upside down and backwards from each other. So I must choose to multiply one of the sides by a conjugate. If I multiply on the left, my conjugate would be of my denominator, and my conjugate would be 1 plus cosine of my angle. On the right-hand side, I'm just going to choose to keep working over here. If I multiply by my conjugate here would be 1 minus cosine of my angle. And a reminder again, because you're treating each side independently, you must multiply by something that equals 1. So on the bottom, I'm also going to multiply by the conjugate. Now, when I do this on the top, this is like a difference of squares that's being expanded. So I end up with 1 minus cosine squared of my angle. On the bottom, I'm going to not expand. If I expand, I end up needing to factor it again anyways. Okay, so usually you only want to actually expand where you are multiplying the conjugate of that thing. Okay, so on the bottom, I wasn't multiplying by the conjugate of the bottom, so I'm going to leave it factored. Now on the top, I can use my Pythagorean identity to rewrite this as sine squared of my angle all over the bottom that I still have. I'm not going to change the bottom at this point. I'm going to extend my wall a little here. And now what happens is I have a sign on the top and the bottom. I can cancel the bottom one with one of the top. And then I end up with sine of my angle over 1 minus cosine of my angle, which is what I had on the left. And so I am done. If I had multiplied by the left side instead, you would need to multiply by the conjugate of the denominator. Which would be by 1 plus cosine of your angle over 1 plus cosine of your angle. And then what would also happen is you would not end up with the answer we got because you'd be simplifying it to make it equal the right. So you would end up with 1 plus cosine of the angle over sine, but both sides would equal that. Okay. So that's all for our trig review. If we went a little too fast, remember it's a video, you can always pause or go back if you need to go through another example again. And there's some practice questions just on the bottom here, and the answers are posted to that online. And also in your Appendix D, there are some extra questions as well if you want. And if you need some practice and refreshers with solving equations and the special triangle stuff, there is the entire trig booklet posted, trig review booklet that's posted that is all trig practice questions as well.